Modern open source modular electronics and fabrication allow us to easily create versatile and precise physical devices, whether they be DIY CNC machines, plotters and 3D printers, or the inverse of this as large-scale precise input devices, such as this slider built from a modified CNC gantry kit with 0.4mm resolution along its range. In immersive environments, physical control is typically performed by mid-air gestures or with handheld controllers. These are limited in their ability to simulate the solid physical properties or the precise inputs that we would expect from traditional physical inputs in the real world, such as the dials on a machine lathe, the sliders of a mixing console, or the controls in an airplane cockpit. Past work has explored the use of fabrication using off-the-shelf components to create tangible controls for immersive data visualization. We explored the use of physical controls mounted on the end effector of a collaborative robot arm, not only to create a tangible controller for immersive data at a one-to-one scale, but also exploring an adaptive physical control surface. In this medical imaging use case, only a single slider control is present physically, but 6 are available in VR. The user reaches toward a missing control, and the robot arm and the DC motor reorientates the physical knob as required. This use case is a virtual reality adaptation of the DIMP-Viz scenario for direct interaction with time series data curves, where the primary interaction affordances are the data points themselves. When the user moves their hand within the axis of the scatter plot, the data point nearest to the user's fingers is highlighted and a time curve is displayed. Simultaneously, the robot rotates the slider knob to the tangent of the curve at that point, and moves the slider knob such that the knob will be ready at the position of the data point by the time the user's fingers reach it. To test the potential for our dynamic robot slider to perform a simulation of the fixed larger scale slider from earlier, we conducted a user study where participants performed a simple pointing task, matching the slider knob position to arrows denoting random positions on a fixed horizontal axis in virtual reality. Users were asked to match 30 values each time with a large one-to-one physical slider, a virtual slider using mid-air hand interaction, and the dynamic robot slider. We found that the dynamic slider was as accurate as the full physical slider, and that both of these were much more accurate than the virtual slider. The physical slider was faster than the dynamic slider, which was in turn faster than the virtual slider. Each condition was ranked by the participants. The fully virtual slider was ranked as the least preferred technique, and the full-size physical slider was ranked as the most preferred technique. The most common comment for the physical slider was that it was the easiest to use with minimum learning effort required, and that the pointing task seemed pretty effortless. More than half of the participants commented that the user experience of the dynamic slider is somewhere in between the physical slider and the virtual slider. In future work, we would like to explore expanding the concept and with different hardware configurations, for example, in versatile control panel and tangible user interface simulation, and with wheeled robots that can move around in the virtual environment.